Everybody, welcome to the presentation of our paper, Enabling Green Content Distribution Network by Cloud Orchestration. This paper is going to be presented in the SCNS’16, the third Smart Cloud Networking System Conference. The authors are a group of researchers. Dr. George Collins, from professor in the Colorado State University. Dr. Dubo is a cyber team leader in Fulcrum. Dr. Pastricha, which is my co-advisor in Colorado State University, and myself. Yahav, I'm a PhD candidate at Colorado State University and a program manager in Microsoft Azure Compute team. The outline of this lecture is we're going to first of all talk about the problem, which is an ever-growing carbon footprint by data centers. We're going to talk a little bit about the characteristics of on-demand streaming as a cloud workload. And we are going to see if we're going to look at a few possible solutions, and which is a cleaner power mix. And we're going to talk a little bit about why on-demand streaming as a workload that we choose to focus on in solving this problem. And then we're going to talk about how can we use green energy, and essentially I'm going to share with you the prototype that we did and the results. So as for the problem, ever-growing carbon footprint by cloud computing is something that that already exists since the evolution of the public cloud, with all the offerings, SaaS, software as a service, infrastructure as a service, and platform as a service. They are all variations that essentially form what we know today as cloud computing. Those services are manifested through data centers, and data centers projected to consume approximately 73 billion kilowatt hours by 2020, with corresponding increase of greenhouse gases. So this is one aspect to it, and then more and more governments are starting to initiate or to impose a carbon tax on IT organization to encourage major cloud service provider to pursue green energy opportunities for their data center operations. And so today, most of these cloud service providers, CSP I call them in the paper, are operating with zero-sum game fashion. They are competing with each other. So there is no cohesive system existing to coordinate the rising data center energy demand with the rising green energy supply. Just to give you a quick context on the work, on the broader perspective of the work, is that we are suggesting a collaboration game between the cloud service provider when utilizing when processing the video on-demand streaming. Essentially because that it's already shared, and we're going to talk about a little bit more in the next few slides. So I guess that the problem is that we have lots of energy projected to be consumed, and this energy will be processed for a specific workloads, and we want to optimize it. On-demand streaming. On-demand streaming content is managed and distributed by content service providers, which is Amazon Instance Video, Netflix, other over-the-top providers, and they do it by caching and distributing it using something called CDN, which stands for Content Delivery Network. Those are located on the edges of the internet network, which with proximity to the consumer. So the canonical example is that if you have a video that somebody published in YouTube and there was a lot of views of this thing in a specific area, this specific video will be distributed into and cached into few CDNs that are on the ISP data centers, the internet service providers. So when a consumer will want to stream it, they will not have to stream it all the way from the originator, a CDN or a website or service. So it's basically a way to optimize the distribution and bandwidth, of course, which is playing a big role in the cost structure of this business. CDN service providers support a seamless integration with cloud-based object storage that pipeline the digital content from the organization site to the CDN instance that runs at the internet provider edge, which is so essentially what we're saying here is that the CDNs already have already hosting object storage that is located on the cloud provider. So essentially what we need to do in order to optimize this experience is basically just to connect the CDN edges with the cloud service provider, and combining the two facts that those are located close to the consumer, you can optimize the user experience. Another characteristic of on-demand streaming is the HTTP chunk-based streaming protocol. Its support is supported currently in CDN. It allows the client application sufficient time to detect the optimal CDN instance to handle user workloads. And just to give you an example, so if you are about to initiate a streaming session, the client will contact some FQDN, a domain name service. It will, once that it's going to start negotiate with this service, it will, before it will start streaming the video, it will download a chunk of the clip, and then once that this chunk is downloaded, and started to play, while this is playing, the chunk is playing, it is going to download another chunk. So the HTTP chunk-based streaming protocol basically allowing us to have and to make good decisions around how and from where we wanted to stream the video, and it's basically eliminate the real-time notion of the streaming experience. So with that said, that when we have this chunk-based protocol, downloads or streaming protocol, we have a time to make a decision. And now let's talk about how can we use this time in order to optimize this problem. A system to accomplish a cleaner power mix will have to provide seamless failover in the case of sudden interruption of green energy to grid energy sources or vice versa. So what we're trying to say here is that if we have this time, and let's assume that we have a system that can tell the client, hey, go and start fetching the next chunk, HTTP chunk of the video of demand content, we can opportunistically be biased towards the green energy instances. Behind the scene, we will have to build a system that will employ such green energy. So employ an application buffering schema that better allows the for opportunistic green on-demand streaming processing, which is essentially what I just said. It requires an extended, cohesive, federated system that aggregates supply and demand across multiple geographic locations, employing the smart grid command and control infrastructure to achieve an optimal dynamic matching of green energy sources and computing loads. So basically, we are saying here is what you have today is that you are using by default the smart grid command and control infrastructure, right? And what we are saying is that we will allocate a specific workloads on the cloud provider on the edge that might run on a clean energy or green energy, as I call it out. And when we want to fail over from green to grid or from grid to green, we will rely on the application buffering schema that we called out before. Why on-demand streaming is an interesting problem. On-demand streaming constitutes up to 85% of the internet traffic consumption. So what I'm trying to say is that 85% of the bandwidth going from a service to a consumer, to the end consumer, is devoted for on-demand streaming. The rest is live streaming, which is mainly news and sport, and the rest is web browsing as we know it. 85% of, just to give you an idea of what we are of what we're trying to optimize here is this type of streaming will generate approximately 34.5 gigawatt an hour per year. And what we see here in figure 1 is basically the pattern of how this load is distributed. And we can see here that, and this is again, it's optimized across several time zone, but essentially consumers started to pick up, started to use on-demand streaming for work and for and for private purposes. Started at 10, it's growing, and it stay like that until around a 8 or 9 p.m. 9 in the evening. Green energy utilization is hard, and why is that? It is basically we are focusing on two sources of green energy. One is solar, and the other one is wind. We ignore the hydro, because hydro is a much simpler problem that has is currently well utilized as, in the green in the smart green, and it's also integrated with high fidelity as opposed to solar and wind energies. Few of the problems that wind energy provides is frequency stability in wind power and availability and frequency stability in wind power. So essentially, once that we have a wind energy, it's not enough. We need to classify this this availability through three main milestones across the availability period, and we call it cut in, rated, and cut off. Even though that we have before the cut in a viable enough viable amount of wind, we cannot use it until we reach the cut in point. And also when the cutoff phase is coming, is in the cutoff phase, we have to stop using the energy, because we believe and we know that the wind will go off and will stop generate viable energy. And when the wind is and so I guess that the effective portion for actually utilizing a wind energy is between the cut in and the cut off, and a big part of this range is called the rated, which is the part that we can actually use the wind for electricity distribution. Something very similar in solar. Solar is a little bit different, but I guess it follows the same pattern. Here we have efficiency and daily hours of availability of solar power. That it's basically depends on the clouds, depends on the temperature, and it follows a very similar patterns. There we have the cut in and the cut out, and if we don't have any sudden of a cloud that is covering the sun, we can get a good signal. Clean power mix for on-demand streaming. We argue that based on the green energy's volatile nature and the on-demand video streaming workload characteristic, the optimal resource allocation approach should be opportunistic. We propose a multi-cloud resource coordination system that matches computational resource demands with available energy supply to maximize the utilization of green energy for processing cloud workloads. And this is an example of our suggestion. We are saying that, hey, we are going to allocate a portion of, identify a portion of the processing capacity in a data center, and we are going to run opportunistically some of the servers on renewable energy, and we are going to make the assessment and the scheduling of saying that one server that runs on renewable will start while the one that runs on grid will not process and will go into some hibernate or into some kind of a sleep mode. We are going to coordinate it through a coordination system that is based on some of the state-of-the-art systems that we have today in cloud computing. So the prototype simulation, basically what we did here is that we created such architecture, and this is what we generated. So on the top graph you see a green energy availability simulated in megawatt across regions. So you can see that there are these are the solar. The top one is the solar availability, and you can start that in one zone the sun is picking up at 6, and then at 6 a.m. and then it picks up and then on the other on the US East solar farm it picks up at 12, and then basically it follows 48 hours of cycle. The same thing we simulated in the wind farm. This was in US west wind and US central wind and US east wind. Those assumption was made based on NERL measurements, NERL measurements that was done in those three areas. So what we did is that basically, based on those availability, we started to generate demands that convey the demand that we showed here. Okay, so essentially this graph that is based on Akamai data indicates the demand, and this is the data that supports the supply of the energy. And what we see here basically is the simulation where we created a match between the demand and the supply. And essentially every session that we were able to run while we are using the green energy, the clean energy, the wind and the solar, it was measured as a benefit. So what we see here is a video on demand user workloads per region adjusted with user population, opposed to aggregated green energy availability, solar and wind. And these are the results that we got. The scenario described above simulated the usage of 80 of green 801.3 kilowatt per hour, kilowatt hours out of total 3,642 kilowatt hours to process the video on demand streaming workloads. Counting the utility per region, we wanted to have a realistic result. So what we did basically, we distributed the load based on the population. So US West used 42% of the green energy, Central US used 28% of the simulated energy, and East US utilized only 18%, as the initial ratio between the user demand and the green energy availability was relatively low. Although West US reached 40% utilization because of the availability of wind in the specific area according to NERL, our source, it contributed only to the 20% portion it contains from the entire experiment test set. Okay, so we were trying to do some optimization and be more realistic. So essentially we didn't declare 40% utilization, we declared 22% utilization of green energy by opportunistic matching only. If we are extrapolating the simulation results to the initial assessment, we were able to show that we can optimize, regardless to the carbon footprint, we can optimize the cost by $759,250 US dollars per year. Yeah, that's about it, and I hope that you find it interesting. Thank you very much.